Q, and then probably here I shouldn't be writing very close to the bottom of the chalkboard. So here on that part I have more flexibility, okay? But if something is not that well seen, feel free to move. There are plenty of seats in the first row. So if it's for your learning, so of course, try not to make too much noise, but you are most welcome to move closer to the chalkboard. And I instructed Freeze to make every effort to record everything which is on the chalkboard. But I'll provide my lecture notes in the due course. Okay, so and please keep in mind that there are announcements made from time to time, hence you need to pay attention to course page and check it regularly, okay? So anyway, I was being emailed on various things, on what specific parts of 5 textbooks I'm going to use. Of course, there is a huge overlap between some books. Yeah, so some books are simpler, some are harder. Yeah, so but that's what is to be expected. So for this lecture, and then I put recommended reading on lecture notes, so you'll have it in the lecture notes. Okay. So first of all, there is the book by Patrick Billingsley. It's 4th edition. So it's chapter 1, section 2, which is kind of hard. And I made Scarborough Library purchase electronic version of 4th edition. It is already available online, yeah, but you need to get to your library account, yes, so, and read it from the library page. It's not publicly available. It's available for UTSc community, and also there is a hard copy which I moved from Math Sciences Library in St. George campus to Scarborough Library. It's on reserve, so if you want to read hard copy, it's okay. And our CMS librarian promised to purchase another copy for Scarborough Library, okay? But it's not an easy book to read. It's more like graduate level, but there are basic things which are over there also, yeah? So then there is a nice book by Gnidenko. And it should be chapter 2, section 6, pages 37 to 43. It's easier to read. But English translation is not that polished. I would say that Gnidenko, who was my family friend and departmental chair during my graduate studies, so he was one of the most senior students of Kolmogorov and succeeded him as chair of the Department of Probability Theory at Moscow State University, from which I graduated from. So therefore, his exposition of Kolmogorov's approach is much closer to Kolmogorov's original ideas, which go back to 1932 when he was a visiting professor at the Göttingen University in Germany. From this point of view, reading Gnedenka's book should be simpler. So he was an excellent speaker, a perfect writer, a very, really a great person. But the translators of the most current edition of his famous textbook, which was translated into numerous languages, so it's not that perfect. Still, it has main mass ideas, so the translation should have been, of course, polished. But the same book has a perfect chapter on the history of probability theory. Gnedenka was a math educator, so he was interested in speaking to freshmen, taught a course for freshmen, and he also worked on the history of mathematics. So, and you might be interested to read about it. And he exercised some influence on my research and my education skills, although he wasn't formally my PhD supervisor. So anyway, I would recommend you this book. So I'd say it would be the right level for this course, although I add more measure theory stuff than considered in Gnedenka's book. So, and the third, and here you can see everything, I hope. Yes, so it's our first meeting in 309, so I hope you can see it, yeah? So, but in Evans and Rosenthal textbook, which is really a star B52 book, there are challenges. And advanced topics. And one of them is theorem 161, which is such advanced topic that I'm going to mention in the due course today. And the fourth thing is Ross, a first course in probability. What you need to consult would be section 2.3, which is actually not covered in this course, but it's a kind of review of what you might have heard in star B52. Yeah, so, but this section 2.3 from Ross' book is too elementary, but a good starting point. Can you see here? For review. So can you see it here? Yes, you can. Okay. So therefore, you might want to start from Ross for elementary review, and then there are other sections and chapters from more advanced books that you might want to consult. So, of course, read my notes. And I hope my writing is clear enough. Okay, so you have access to my lecture 1 notes. So I hope you were able to read them. Okay. Now, so S or omega, so this is the last letter of Greek alphabet, which is frequently used in probability theory. It's an arbitrary space or set of points which we denote by omega. So, and this is the lowercase omega. So it's the last letter of Greek alphabet, which is common to denote the sample space. So it's in this part of the world, it's more capital S, which stands for space, though. Okay, so S or omega is the universal set in set theory, and the sample space in PT, which stands for the probability theory. So this is the first thing that we should start from. Then we consider a certain class or collection of subsets of S, which should possess a certain structure. Which is to be discussed later. So it's the first thing is we need to define the sample space. The second thing is we should identify a particular collection or class of subsets of our universal set or the sample space. In probability theory, they are called events. So this will be denoted by script F. And the third thing is we should introduce a certain function, capital P, from our class of events to the unit interval 0, 1, which has particular properties. And we need to make a big breath now. Come on in. Get closer. Okay? So there should always be 3 things to be considered So it's a universal approach to tackle all the problems of the probability theory. For each probability model, we are to determine three things: the sample space, the set of events script f, and a certain function, which is a function on the sets. So for each event, we ought to assign a certain number between 0 and 1, which of course will be interpreted as the probability of such event to occur. And of course, we need to discuss what kind of structure this set of events should have, what problems could incur, and of course, we need to specify the properties of all probability functions. They cannot be arbitrary. Okay? And at this stage, I want actually to discuss the axioms on this part 3. I want to discuss Kolmogorov's axioms imposed on the probability function capital P. So, please, so you caught this stuff already. I can erase it, yeah? Thank you. Okay. Yes.
Here. Okay, I have two
Michael, yeah?
to clarify. The first is like, what is PT in the axiom?
Yeah, it's probability theory. You are expected to watch my videos. Yeah, so it's probability theory, okay? I don't always write it.
And the
Yes.
axioms are those 1, 2, 3.
No. These are the standard things. The axioms are coming up. Okay? And it's just the list of things that we need to describe when trying to solve any problem of probability theory. We ought to determine these three things for each probability model. So it's just an approach to kill multiple birds with one stone. Instead of solving each individual problem from scratch, it is more convenient to make an effort at the very beginning and develop a certain approach that is going to be universal for probability theory. Is this clear? Okay, so, and that's what I'm doing now. Now I'm trying to be more specific and describe properties of the probability measure. So, 3 Kolmogorov axioms are as follows. Yes, so the first one. For each event H, there is an associated number P P of A which is always greater than or equal to 0. So this number is, I should say that it's non-negative. Some of you might have seen this axiom in slightly different form, namely that P of A is greater than or equal to 0 and less than or equal to 1. For instance, this is the case in Ross' book. However, this upper bound is not necessary because it is obtained as the corollary from the three axioms, and I'll comment on it in a few minutes. But this is not a unique way to present the axioms. This is the original way to do it. Okay, so the second one is often called the assumption of unit measure. And it means that probability of the whole sample space is always 1. So always 1 or 100%. Yeah? So therefore, the sample space is called the Sure event. S is the Sure event. And I know you make notes, which is, of course, encouraged. But if you can just stop for a moment. Yeah, as you notice, I don't erase this stuff right away. Yeah? So it's like a very general comment first. If you want to develop something new, you ought to impose some constraints. So getting something nice, especially at the very beginning, always requires some constraints to be imposed. Understood? It's not only for probability theory, it's for any other branch of math. And in order to develop probability theory into a separate branch of mathematics, some assumptions had to be made in order to make rapid advances in the development of the theory. Understood? And for PT, there were two such major assumptions. One was this second axiom, that the probability of the whole thing is 1 or 100%, because it's a measure and there are other measures. There are even signed measures. But here we always have that total probability is 1. Okay? And the other assumption or the other restriction that helped develop probability theory into a separate branch of math was the concept of independence, which you heard about and studied to a certain level in study 52. Yeah? So, and of course, later, the assumption on independence was weakened. But these were two key constraints which gave a boost to the development of probability theory. Is this clear? Okay? Now, I want to erase this stuff. Okay? Okay, and the third one is sigma additivity or countable additivity axiom. Of course, you can see it, yes? So I hope I don't try too high. You can get it, freeze, yeah? Okay, so you know this Greek letter sigma, because in probability and statistics, the same letter is used for standard deviation. Okay? But for now, it's actually the concept borrowed from other parts of mathematics, say analysis and algebra. Okay? So in algebra or analysis, it's used, in set theory, it's used for something else. And we borrowed this concept in probability theory. So sigma additivity is something that migrated to the theory of probability. It's not something unique for us, but it's something very important for you to learn. Okay? So it's also known as countable additivity, although this terminology is quite common. Yeah? So anyway, any countable sequence of events A1, A2, A3, etc., which are pairwise disjoint satisfies the following identity. Namely, probability of countable union over I from 1 to infinity of AI equals the sum of their probabilities, P of AI. Now, I checked the terminology. So in Gnedenko's book, it's pairwise disjoint. So I hope you remember that disjoint events are those which have nothing in common. So often it's called disjoint events. Yes, so this means that AI cap AJ is empty for I not equal to J. So it's basically the same thing as disjoint events, but we deal with pairs. But when we are going to consider independent events, then for independent events, there is a difference between pairwise independence and total independence of the set of events, as some of you might still remember. Okay? So now let's take a look at this additivity. I should say it's called sigma additivity. And there are versions of this third axiom. For instance, some write that any finite or countable. Would it be true? Of course. Do you have to impose this additional constraint that it's for finite or countable? What do you think?
You don't need finite because you can let infinite to be the empty set. So
Yeah, but it's okay.
yeah.
Empty set is okay. No, but it's going to be true, but we can get it as a corollary. That's the trick. And I don't know, are you reading about history of math, some developments, say, of non-Euclidean geometry? So there are pure math majors, although as I learned this morning, the number of pure math majors frequently goes down. Yes, so for applied math majors, you probably are not that interested in proofs, but this is the course where you need to learn the proofs. Say, for Euclidean geometry axioms, there were enormous efforts made to see if they can be weakened or if something can be derived from something else. Yeah? And then during such studies, it was actually discovered that if you want to live in the Euclidean world, these constraints or these axioms are all needed. Yes, so if you weaken them, then you get something else. Okay? So, and then the same idea actually here. Like you need, in order to get something meaningful in math, you ought to find such a minimal set of axioms. You shouldn't be asking for too much at the very start. Does it make sense? And hence, you shouldn't be asking that P of A is less than or equal to 1 as an axiom, or that it is true for a finite or countable. Because you could get these results as corollaries from your minimal set of axioms. You ought to find the right number of assumptions, not asking for too much and not asking for too little. Understood? So it's a general comment, and it's applicable not only for the mathematical foundations of probability theory, it's true for other branches of mathematics. Yes?
Professor, do we have to mention that the empty set is an even?
We'll talk about empty set. Don't rush up. Everything which you learned in star B52 will be needed. Of course. Okay? Now, so we spoke about probability measure. Now it's time to discuss this collection of events, script F. So laws of probability, which you learned in B52, they will all be needed. We are going to prove them from these axioms. Understood? It's exciting. you will no longer need them for granted. You will be happy when you are going to be able to derive them from scratch, from these three axioms. Someone did it for us, but you would have to redo it to acquire your expertise in probability theory with some measure theory, okay? But keep in mind that it's what was done actually, it was just done 90 years ago, okay? Of course, yeah, I witnessed the last 9 years of Kolmogorov's life. Okay, so when he accepted me to his residence school, he already was 75. When I graduated, this was actually the same year he started developing Parkinson's disease, which killed him in the fall of 1987. So I didn't witness him in his best years. Of course, I watched movies about him. I studied with his students. So he himself didn't teach me probability theory. Believe me or not, he taught me elementary calculus. But there are still a couple of things which I remember in the very first lecture on elementary calculus. He taught us how to solve differential equation y prime equals ky. It was a little bit too much for the first lecture, though. There were other things which I remember, but nothing was heard from third row during his lectures. He didn't use the mic, so his voice was already very low, but he was still jogging around the dorm. Yeah, so at 74, he was still active. He was actually a big fan of cross-country skiing. So if you are interested, one of my friends and colleagues from his former chair of finance at Schulich School of Business, he wrote a chapter of Kolmogorov's work, which I would be willing to forward you to read. Yeah, so it's about importance of Kolmogorov's work in finance and insurance. But anyway, of course, these were ingenious observations that boosted the development of probability theory. Okay, first of all, so it's claim, not every subset of S should belong to this class script F. And to convince that this is the case, I want to provide a counter example. And the counter example is the continuous uniform 0-1 distribution, which you learned in B52. Yeah? So we say that random variable x is uniform 0-1, so some saw it as tilde, meaning that random variable x has distribution uniform 0-1. So it's not equation. When I write little d on top of the equation sign, it means that distributions of two random variables are the same. It's different from saying that random variables are the same. Okay? So if you deal with a random variable that is continuous, uniform, 0, 1, so it means that probability of x belonging, say, to closed interval a, b equals b minus a, where a is between 0 and 1, a is less than or equal to b, and b is less than or equal to 1. Yeah? So the reason why it's called uniform 0, 1 is because the probability or measure for our random variable to fall to a particular interval from 0, 1 equals the length of such interval. Is this clear? Okay? So, if you do it, and of course I can include left and right hand ends, it's not going to make a difference. Yeah? So I consider such a model, and there is a remarkable theory which I'm not going to prove, but I just present it. So what actually happens is that there does not exist a probability measure P of A defined for all subsets of 0, 1, which would satisfy all the three Kolmogorov axioms. Hence, we cannot be too general. We ought to impose a structure on this set of events. We are not able to consider all possible subsets of our sample space and introduce a probability measure that would satisfy all the three Kolmogorov axioms. Sometimes it might be possible, but not always. Understood? And the structure of such a collection of events is actually borrowed from other parts of math, analysis, set theory, and algebra. Okay? So it's the definition of sigma field or sigma algebra, which are the same things for probability theory. So is as follows. So first of all, we have a kind of sub-definition of a field. There are three requirements, namely the whole sample space should be a member of such a field. The second requirement, the fact that event A belongs to a field implies that its complement is also a member of this class. And by the way, this answers your question. Yeah, complements came up in the definition of a field. So hence, if we know probability of event A, we would be able to find probability of complement to A, and we'll rederive the law of complement, of course. And the third requirement is that the fact that two events A and B belong to a field implies that their union also belongs to this field. So the fulfillment of these three requirements implies that it's a field. But if you impose the fourth requirement, so this would be a field. So if you imply the fourth requirement, that if F is closed under formation of a countable union, we get a sigma field or countable field. So this property 4 means that the fact that A1, A2, etc. Belongs to this sigma field F implies that their union, the countable union, also belongs to this sigma field, and hence we should be able to determine the probability of such event to occur. Then what you will read in Gnedenka's book is, for instance, this can be replaced by an equivalent assumption on continuity of your sigma field, which we will be discussing. Evans and Rosenthal book contains slightly more general theorem known as continuity theorem. Okay? But the class is not over yet. Please be patient and attentive. So we will talk about this stuff and solve some problems. But I want to summarize what we did today by introducing the concept of a probability triple. So for each probability model, we need to have probability triple comprised of these three things: S, script F, and capital P. And this is how we should deal with each probability model. We ought to come up with this triple, and I should comment that for the same sigma field, there could be several probability measures. So, therefore, sigma field is primary as compared to the probability measure. Is this clear? So, and more information is given in the notes, but it's time for us to finish. And let me take your question. But, yeah, S is the sample space. And let's thank Freeze for recording.